Today we're going to do section 7.8. No, sorry, 6.8. Let me fix that. All right, so let's scan the old page that we already scanned. Okay, let's see. Here it is. And then a bit closer on top and a bit closer on the bottom. That should be good enough. Next, page 208 and 209. Let's see here. All right, that is the full page. And then a bit closer on top. And a bit closer on the bottom. Okay, that should be good enough. And next page, this is 210 and 211. The last one. We will also zoom in on top a bit and on the bottom. Although I guess we don't need the bottom till next time. Okay. So let's start on page 206 and section 8.1. Now, f is defined in the closed-bounded three-dimensional region. So now we were doing the 2D situation, okay, integral of double integral. Now we're going to do the triple, so one more dimension. So our domain of integration is now a 3D object, which is called V. And a V better has some volume, okay? And then we'll define some kind of a subdivision of V. We'll cut it up into little pieces. And then the normal V is its diameter, the biggest diameter of all the little pieces that we cut it into. And so V is divided by delta into subregions from V1 to Vn. And then x, k, y, k, z, k are points in these each one of these little chunks. And then so the triple integral is then defined, as you might imagine, is the sum of function f at those points multiplied by the little volumes and sum it all up, and that will be the triple integral if the limit exists. Now the symbol delta vk is just the volume of vk. Now, so the one situation we should notice is that the integral 1 does exist if f is continuous in V. Okay, so it's and that is what was theorem 1 again? Let's go back and look at it on page 183, just to refresh the memory. Theorem 1, all right, which states that the function f xy is continuous in the region, some region xy in closed region. Then the integral of f does exist. At least I think it's closed. But anyway, so that is that's just theorem 1, and a similar one, except that now is in 3D. So if f is continuous in the volume, in the chunk of stuff, before it was in the region, now we're in the entire volume, then the triple integral does exist. And also the properties on page 185 all works. The book says that the property 1 to 7 apply here also. Mutatis mutandis. That means that's Latin for with required changes. So basically they all work. Okay, let's look at it briefly. It's all this stuff where all the integrals, it doesn't matter what dimension you're doing the integration over, all the stuff work the same way. This is on page 185. All right, so moving on, we have, so look at the next page, 207. We have, to calculate the double integral, we'll go back to doing an iterated integral again. Okay, And this is possible, but not for any old thing, for a special type of regions that we're going to delve into today, which is which will be called VXY. Now pay attention to this, please. VXY is described as V, R, phi, and psi. What that means is, so VXY is described as something that has an R on the bottom, which is the region on the XY plane, and it goes up or down, and it goes up, and then it gets to a function phi, which is a two surface, okay, and then a function psi, another surface, and then so the thing in between will be called will be the volume. This is a cylinder, that is, everything is going straight up, where a cylinder along the border of R, and so all these excuse me, all these are vertical lines, and that will define the V. So V is has vertical lines all the way around, but on the top and the bottom it can wave around however it feels like, that sort of thing. However, phi and psi for our purpose has to be continuous all the way on the closed region, so it can't go to infinity or something like that. So it's yeah, and we also require phi to be less than psi, okay, so they don't cross or do something weird, and they just, let's keep except on the boundary it's okay that they reach each other sometimes, but generally speaking we'll keep it somewhat simple, okay, then don't let it go nuts, and don't let this thing go nuts on us. And so as a demonstration of this notation, again, please pay attention to this notation, and VXY, and imagine what that means, okay? That's the bottom region that defines it, and then phi is the bottom surface, and psi is the top surface, and all that together will define your volume. As an example, imagine a volume that's defined like this, okay? It has a bottom region R, or R something, yeah, just R. And then the top surface is, the bottom surface is phi is this, top surface is that. Those two are the two halves of the hemisphere, right? And then what is the region? The region is, if you look at it more closely, it's just the units, it's just a circle with radius a. In other words, this region is defined with R in between phi and psi. Phi is on the bottom and psi is on top, and actually it's just a sphere, okay? And whereas the region is right in the middle. And so so please work that out yourself if you're unclear in any way. And then we'll move on to theorem 5. So theorem 5 says, if we have what are we doing? Oh, theorem 5 is to show that the triple integral, we're doing triple now, 3D, the triple integral is the same as the iterated integral. So that's what we're going to prove. Now that might sound familiar. That's because it is, okay? This is identical, nearly identical, except for the dimensions of theorem 2. Okay, which states a very similar thing. That is, which states that the double integral is iterated integral of this thing. Except now we have an extra dimension. So now we're saying the triple integral is the iterated integral of the last piece and over the double integral. But the idea is exactly the same. And also the proof is also nearly identical. Okay? And we're going to go about the proof the same way, which I have the book scanned into my tablet here, so that you can compare the old proof with the new one, being that they are so similar. All right, so here it is. Here's the theorem 5. Let's see, this side, no, the other side, this side. Okay, so theorem 5 is what we're trying to prove. On the other side is the old one. Okay, there's one dimension less, but other than that, it's identical. So what we're doing is we have the function, okay, continuous. We have our region of integration. In this case, it's a volume, but otherwise it's the same way. See, it integrates on the bottom area, and then going up from phi to psi, just like the other side. And And so the first thing we notice, well, this is the conclusion, is that the triple integral is the same as the iterated integral. And you can see the similarity to the other side. Now to prove it, the first thing we're going to do is assume that the phi equal to 0, which is what we did before, okay? And now, so assume phi equal to 0, and then we do the subdivision just like we did before, okay? We'll subdivide the region R into n subregions, all with equal area delta S. See, before we have the region B minus A subdivided into equal areas, all called delta X. So right now, the delta S is basically the same as the delta X before, okay? And then, and then next, we'll define big F x y is equal to the integral of 0 to phi of, from 0 to phi of f, just like before, see? The same thing we did before. And therefore, and then as a result, the integral is, over R is going to be the limit of delta S times big F, okay? That's just the definition of an integral. And so next thing we're going to do, let me move this up a little bit. Now knowing this, all right, now we are going to, similar to this situation where we use the mean value theorem, this integral, we have yanked out the phi, right? We pulled it right out over here. Well, anyway, this thing I'm going to call it, phi, or this is pronounced psi. Maybe I should call it psi. Anyway, we'll yank out psi of x right out, and just like here. See, let's yank it out. Whereas the delta S is the same as delta S. It works the same way as delta X before. Okay, and so that is that. And then next we have, as before, we have some minimum values. Mk is equal to the minimum of phi on some Rk on a small volume, on a small region, just like before, whereas Mk is the minimum of psi of x in the small region. Then we're going to divide the cylinder under psi on Rk into n plus 1 subregions by. So then what that means is that now we're going to divide it like before. That is, this is divided from the bottom up. Okay, so this thing is like that. So we'll slice it all the way up. So you have a bunch of slices, just like before. So we are going to divide it like that into n plus 1 subregions, and by n equally spaced planes. Before we divided it by equally spaced horizontal lines. Now we're dividing by equally spaced horizontal planes from z equal to 0 to z equal to mk minus 1. And you notice the similarity with the previous version. So delta x zk is identical to delta yk. All right. So next we are going to do so each subregion at that point, then each subregion has a volume of delta z delta x. See, before it had delta yk delta x, the same thing. See, the delta zk now is like our delta yk before, same idea. And then delta sk is the same as delta x. Is it just, no, there's no k there. Delta s is just delta s, okay? It's the same everywhere. And so then the volume, except for the volume of the top area, the volume of the top piece is defined slightly differently. And as before, but it ended up, see, looking exactly like it did before. All right, so that is that. So next, I have some formulas copied from the previous page, just to refresh your memory. And this is how we define big F in the last page. So then, which is identical to the one in the previous case. Okay. So then f x k y k will be this sum of stuff, and where delta zk is it works the same way as delta yk before, and the f and the f, and here's the last piece. So we have all this stuff added up, okay, from the first part, just like before. Please, this might look a bit confusing, and so please just stare at this until it makes sense. That's the only way to really understand it. Okay, let's see, my screen is not parallel. Anyway, so something like that. And okay, that seems a little better. And so the next part is the subregion. When we crank out the subregion volume is delta zk delta s, then by the mean value theorem, then we can find some zeta, just like on the other side we find the eta. Okay, and so we find some zeta and yank the thing out of the integration. So we got to this point. Okay, and this is the top piece. The top piece runs slightly differently, just like before. See, it looks even identical. In fact, the book even has an example of this. That is, we have that thing equals to this thing. So anyway, so continuing, we have when I type in all the stuff identically to before, delta S represents delta X before, okay? Delta Z represents delta YK, delta ZK is similar to delta YK, and so on. And you notice the parallel looking formulas all come out to be the same. So we got to the last point. And so what we have right here is that if this is the case, all right, as n goes to infinity, then the magnitude or the diameter, or whatever that is, the magnitude of the delta goes to 0. And so all things crashed into this thing. You see, as the big F here is similar to the big F before, and the limit is end up does equal to the triple integral. So that the iterated integral end up being the same as the triple integral. All right, so that is, I know there's a lot of symbols, but there really isn't much to it. It's just a matter of confirming with the previous proof, okay? Double checking everything is all we're doing here. Since we already proved the previous thing before, and this goes exactly the same way. So please just spend some time staring at this thing until, or reading the book through, okay, until everything makes sense to just work it out. Okay. So continuing, let's go to page 208 and look at example A. Example A tells you to calculate the volume of the tetrahedron, a standard one. And it's so please do this yourself, okay? But be sure to notice what Vxy means. Again, Vxy is that thing that I told you to pay attention to in the previous page. Vxy is this thing is defined right here. Okay, which is drawn by this picture. That's Vxy. This area, right? I mean, this volume right in there. So other than that, so please do example A yourself. Okay, I also did it. Let me show you what I wrote down in case you have any questions, which I don't really think you will have any questions. There's not much going on here, and it's something that I'm sure you've already done in basic calculus, but it's good to do a little bit of this because it will be required in the homework. Okay, this example A will be reworked several times in the homework. So please do that yourself and calculate the volume. And with that, let's go to the bottom, the applications, various applications, mass, okay, center of gravity, moment of inertia. It all has formulas given. Force of attraction, which I don't think we did that in the homework. And then, okay, so then let's look at the following page, 209. Now where all these formulas, the function f represents some sort of density or some other thing. We don't care what it represents, really. It's just a function that's stuck in there. And most of the time, we just take f to be just 1, unless we need specify some other thing. Now the center of gravity in this formula it only gives x bar. That's the x coordinate for the center of gravity. Y and z works the same way. You just slap y instead of x in there, etc. And then the integral moment of inertia is about some axis. R is the distance. Okay, in the moment of inertia formula, R is the distance to the axis of revolution, let me think. R formula what? Solar axis. Yeah. Well, is it revolution? What is the moment of inertia? I don't care. The point is, it's the distance to the axis. Okay. And then in four, stuff is given in spherical coordinates. I did not notice that. That's spherical? I guess so. Okay, not that it matters. There's no homework that I found that has anything that we do that, so we'll just ignore that for the moment. Maybe we'll do it later. All right, so that is that. Okay, we have come to the end of this section. For homework, please do problems, I guess this is correct, but let me write it down first. Now for problem, for homework, please do problems on page 208, number 1, 2, 3, 5, 8, 10. Now for problem 1, it's asked you to do the problem 6 ways. Let's just do it one way, okay? I don't want to do it 6 ways. And then problem 5 is something about doing it 5 or 6 ways too. Just do VXZ, okay? That's all I'm going to do. You can do more if you want, of course. But, and why do I want to do the stupid thing 6 ways? It's all the same. And so, yeah, so that's it. So please go do your homework. And when you're done, I want to talk about them. Okay, so for problem 1, we're supposed to calculate the moment of inertia. That's just a matter of plugging the right thing into the formula, okay? It just have to plug in the R there. R in this case is R squared. R squared is y squared plus z squared. And once you plugged it in and worked it around, then the answer is this thing. Or if you use the back of the answer, use the mass. So then equal to mass times that, because the mass is ABC over 6. I've written on top there. And you might figure, wow, how did you do the math so quickly? Do the integration so quickly? And let me show you exactly how I did it by using the calculator. Okay, here's the integral calculator for problem 1. I typed it in right here in the Wolfram calculator. It won't let me type in c squared. If I type in c squared, then it assumes it's the speed of light, which I don't want it to do, okay? And so then it went nuts over the speed of light. So I just type in W with W representing c squared, and then so it was able to get me the answer immediately. Then I replaced W in there, and then the answer popped out. Very nice. So that's problem 1. Problem 2, we are supposed to do, what's problem 2? Center of gravity, all right? So to do the center of gravity, I have, center of gravity is a matter of slapping x in the formula, right? Of the same thing, we're doing the same thing. And so x will be equal plugging everything in with an x. Don't forget the x. And then do the integration. And I quickly came up with the answer x bar equal to a over 4. And by symmetry, then y bar will be b over 4 and z bar it will be c over 4, and that does check out at the answer of the back of the book. And the way I did my integration so quickly is the same secret. Okay, here is for problem 2. Let's move it up a little bit. There we go. So I typed in all that integration. It's not hard to do this, strictly speaking, I guess, but it's even easier if I just type it in here. But well, anyway, yeah, so I just typed it in, and out comes the answer that worked out very nicely. So it's, yeah, and then, of course, the answer has to be divided by the mass, but otherwise, it's worked out fine. Okay, so that's problem 2. Problem 3, I believe we don't have an answer at the back of the book. Nope, but I chose to do it because it's still it's a pretty standard problem, I think. Finding the this density distribution. We just plug it in, okay? And so I plug this in, and the answer popped right out. And the question is, how do we know this answer is correct, okay? And so what I did is, so first I used the calculator to do the integration, because I wasn't going to do that. Goodness, I mean, who wants to do that when you can, all grunt work? And so I did the, and so this is what the calculator says. A equals to A5, and then with the constant. So we slap the constant on there, but so that the constant of proportional constant. But how do we know the answer? So I Googled the answer. The answer, it says the mass of a cube with edge length A and density rho equals to kx squared plus y squared plus z squared, and where the vertex is at the origin equals to m equals to k5a, just like I said. See, so that is about as good as the answer at the back of the book that I got it right. So that is problem 5. Okay. All right, next let's consider problem 5. But however, before that, I want to show you, I forgot to show you before, nothing serious, just in example A, I did the integration on the calculator, and it gave the right answer for example A. Just want to show you that real quick. So that's all. Then, and so let's look at problem 5. What was problem 5 again? It is, okay, right. We're supposed to do something here, okay, which is it's not particularly exciting, I guess, but it can be confusing. So the best way to do it is probably just draw the graph. Here's the graph, okay, and from 2 angles. That's the cube, and then we have to look at the shadow. That is, we're calculating it xz. That is, we're considering the shadow on the xz plane, what it looks like. So focus on the shadow, okay? I have it from 2 angles, and so once you get that straight, clear in your mind, then the whole thing becomes the answer becomes comes easily. Let's see right here, okay? I just wrote it in 2 lines, and xc, right? Then is the v described going from z to x, and then where the r can be either rx or rz, I think. Why would it be rx or rc? Whatever. The point is that the r is described as that shadow on the xz plane, and it's described. Well, the book chose this answer, so let's focus on that one. Described like this, whereas z goes from 0 to a, and x goes from z to a. That's all I can say about that. And so that's that. Next, let's look at problem 8, which says, what does problem 8 say? Problem 8 says, can't find it. Problem 8. Okay, describe this region. Okay, so the best way to describe the region looks a bit confusing, but once you just pull out the Desmos 3D calculator and plot the thing, okay? It'll look much better once you plot it. And here it is. Okay, once I plotted it, here's what this thing looks like. Right, it's just a cone, right? It's a cone sitting on the unit circle as its base, and its vertex is at 0, 1, 0, and yeah, there's nothing else to say about that. So that is that's that. All right. So then that's problem 8. Next, let's consider problem 10, which we have. Oh, we're just trying to calculate the center of gravity of some odd object. All right, so then the center of gravity of this thing, we'll just plug it into the formula, and I'll show you the formulas that I did. I used the calculator to do it. Okay, we don't have the answer to this, but I feel the answer looks good to me, because I was guessing the answer at about 2/3. Now the answer turned out to be 3/5, so it's similar to my guess, which make it sound about right. I'm guessing the center of gravity is something that which go through where if you imagine yourself balancing it like this on an axis, you know, and if it balances, then it's the center of gravity is in that vertical line. So that's how. So I was just imagining balancing that thing in my mind, and to figure out where x bar is. And I also calculate the z bar. That is the center. Even the book didn't ask us to do so, but let's do that anyway. You just plug in z instead of x in the formula, and the whole thing comes out. And that is a little smaller than I expected, but sort of makes sense. So I will just accept that as the right answer. But we don't have to do that anyway. So, and I'll also show you the graph of this object, which I plotted in Desmos 3D. Problem 10, there it is. All right, see, this thing looks, Desmos, it looks really cute, right? It is an object that looks like that. It sinks in. Okay, this is the back view. This is the side view. See, the blue part sinks in there, and dips in a little bit. So it's similar to a slice of a cylinder that's cut. Except that there's a little bit dipping happening right about there, which yeah. And what does that do to the center of gravity? Not sure. Anyway, so that, well, in any case, that is what this object looked like. Okay. Oops. So here is how I plotted it in there. Yeah, normally in Desmos, they will give, when you plot stuff in, you will have all kinds of graphs that extends every direction. You can use these bracelets to limit the graph. See, that way it stops, so you can see your object better, instead of having all kinds of extra pieces sticking out and confusing the view. So you see the blue thing? It looks awesome, doesn't it? So I'm very happy with the Desmos results. This is plotted in Desmos 3D, and just with those two formulas, and also zoomed in into the right angle. So that is that. And the next, I want to show you the integration that I did on the Wolfram calculator to get all this stuff. Okay, here's the integration. As you notice, the integration was done with all the variables in there and was able to do it just fine. I think that first I calculated the mass, okay, because you have to do the integration and then divide it by the mass to get the right answer. So that is for x, and then the bottom one's for z. As you see, I just slap y cosine. Well, anyway, I believe it all works out okay. So that should be the end of this section.